And we're back. Today, the focus will be on the two major routing algorithms, namely link state routing and distance vector routing. So we're administrative. We don't have anything due today, which is Thursday, but we will have a new assignment pushed out, and please stay tuned to the Slack channel for when that will be due and what the details of that assignment will involve. So where we last left off, we talked about major categorization or classification that you use to discuss the performance or the factors influencing a routing protocol. And so we talked about, let's see, is this still recording? And so we talked about whether it is a global or decentralized algorithm, meaning the information that it gathers. And so global algorithms are such that all the routers have complete information about the link cost for the entire network, this so-called topology. And link state algorithms do this. They gather all of the quote-unquote link state, i.e. the cost or traffic or congestion conditions associated with every link on the network. So-called decentralized routing algorithms, the router knows only about physically connected neighbors. Those routers that share links with you are the only routers whose associated link costs that you know of. And with the decentralized version of the algorithms, they engage in an iterative process of computation in which you exchange information only with your neighbors. And so-called distance vector routing algorithms, which is the second type of algorithm we'll study, are so-called decentralized. Another consideration concerns this idea of static or dynamic, how things change. Now, for static routing algorithms, the routes change slowly over time, so they're relatively infrequently changing in terms of when you recalculate routes, i.e. because of traffic conditions. Dynamic routing algorithms are those for which the routes change more quickly. So there are going to be periodic updates, and these updates will trigger different route calculations, and this is in response to having the link cost change. So if traffic goes up on a link, all of a sudden some signaling will happen, and the routes will get recalculated. Okay, so let's continue on. Now, for link state routing algorithm, the major algorithm operates on a graph, and it's called Dijkstras Algorithm. And it takes the network topology, and it takes the cost, or gathers the assumption is that the link costs associated with all nodes are known. And so if you are a node on or a router on the network, you will be broadcasting your link state through a so-called link state broadcast to all the nodes on your network. So this, as you might imagine, is a tremendous amount of traffic. It is, and that's one of the limitations of link state routing algorithms. So let's imagine, let me select a pen, let's imagine, for the sake of consideration, that you have a network, and these are your routers. You have this router, you have another router, let's say you have 4 routers. And these 4 routers are interconnected with one another. So with this link state broadcast, essentially, well, this router, let's label them A, B, C, and D. And so with link state broadcast, router A has no idea of the status of these links between B and C and between D and C. And so this link state broadcast means that C, let me change the pen color. Nope, not going to allow me to do that. Let me try the mouse. So link state broadcast means that router C is going to broadcast its link state to every single router on the network. Likewise, router B is going to do similarly. B is going to send its link state to A, D, C, and D. And likewise, D is going to send to A, C, and B. And A is going to send to B, D, and C. So this link state broadcast means that every single node will have complete information of all of the link costs on the entire network. Okay, so let me switch back my pen color here, blue. So then once all of this link state information, the complete topology of the network, is collected for at every node, and I'm going to use the name node and router interchangeably as synonyms. And so once each node or router has the full topology, all of the link costs for the entire network, it then computes least cost path using this Dijkstra's algorithm. And then once Dijkstra's algorithm halts or finishes, it then sets the forwarding table for that particular node. So node A is going to collect all the link state broadcasts of all the other nodes in the network, B, C, and D. It's going to run Dijkstra's algorithm, and then once Dijkstra's algorithm running on A completes, it's going to install a new forwarding table to impact the switching decisions for router A. And so this is an iterative algorithm, this Dijkstra's algorithm, and after some number of iterations K, it's going to know the least cost path to K of the destination nodes. And so it updates that for each round. The least cost path for another node is going to be known. So it does it minimally, least cost path, one node at a time. So let's focus on some notation. So we have C of xy, the cost function, and the cost function is the cost from node x to y. Now here, the first parameter is x, second parameter is y, and if two nodes are not directly connected, they don't share a link, then the cost is going to be infinity. So say we have a network A, B, another router, C, and D. Okay, so let's assume we have some link cost. That's a link cost of 1, 2, 3, and let's call that 4. So the cost to get from A to D, that link cost is going to be 4. The cost to get from A to C, that link cost is going to be 1. But because they're not directly connected neighbors, cost to get from A to B in this example, that's going to be infinity, right? Because they're not directly connected. So then we also have, for each node in our notation, a distance vector, dv. So it's a distance vector. And let's take a look from the perspective of router A, node A. And so dv is going to represent the cost to get from whatever node that vector is associated with, in this case it's node A, the cost to get from A to all the other nodes, the current cost, because this is going to update. So because we have 4 total nodes, that would be the cost to get to A, so dA. That second position would be the cost to get to B, dB. And that third position would be the cost to get to C, D of C. And then lastly, the cost to get to node D, D of D. So then to get from A to A is going to be 0. From A to B, let's assume that we had already pre-calculated all the paths. That's going to be 1 plus 2, that's 3. So 0, 3. And then to get to C, that's going to be 1. And from A to B, that's going to be going across the top, or rather A to D, going around the along the bottom here, this edge going down, that would be a cost of 4. So what this distance vector represents for each node, the current value, or the working value, you could call it, of the cost to get from the source, that node in particular, to one of the other nodes as destinations. So then we have this P function, this P of V. P of V is the predecessor node along the path from the source to some destination V. So the predecessor is the one that you go to get from that source. So for A, the predecessor to get to C, so for A, P of C, that predecessor is going to be A, right? Because you're going to go through this link. Okay. So That's A. All right. We also have n prime, and m prime is going to be a working set of nodes that we're going to grow one node at a time, each time calculating the least cost path. Okay, so let's take a look at Dijkstra's algorithm. We start out with an initialization, and this initialization starts out, and remember, this instance of Dijkstra's algorithm is running in node U. So we start out with n prime, our working set of least cost path nodes, as being the node that we're starting from, because essentially this is going to give you least cost path from this node to all other nodes in your network, all other routers. So you start out and you look at all the nodes that are adjacent. So for all nodes that are adjacent to the current node running this Dijkstra's algorithm, you're going to call those V. So all nodes V in the network, if V is adjacent to U, then you're going to fill in the distance vector value with the cost of that link between the current node and its neighbors. So if I have a node here, A, and it has directly connected neighbors, B and D, well, that distance vector, D, currently at node A, to go to some other node V, that's going to be filled in. The entries that are going to be filled in, well, I know to get to myself is 0, to get to A, to get to B, to get to C, to get to D. Well, it's going to fill in with 1, to say if that were 1 and that were 4, it's going to fill in DA of to get to B, to fill in a 1 here, and to get to D, it's going to fill in a 4 here, and everything else is going to be infinity that it's not directly connected to. So what this does, it says fill in the distance vector entries for neighbors. Otherwise, set the distance vector entry to infinity. Okay, and that's what we're doing here. So we take all of the nodes and check if it shares an edge with that particular node of question where we're starting, in which we're running this instance of Dijkstra's algorithm. We fill in the distance vector entries for all the directly connected neighbors with those link costs, and everything else, we set those link costs to infinity. So now we're going to do a little bit of a fix-up. We start out and we notice that whenever you have a least cost path, so let's say you have a path from A to some node B to some node C to some node Q, or what have you. If this is a least cost path, by definition of what least means, for this to be a least cost path, that means to get from A to B, this is going to be the least, or the least cost way to get from A to B. This is going to be the least cost to get from B to C, least cost to get from C to Q. So what we're going to do then is we're going to start out and we're going to look at all of the directly connected neighbors. And the reason why you look at all the directly connected neighbors first is because you know precisely what the least cost path is, i.e. the link cost that you share with your directly connected neighbors. And so you start out with that, and then you say, okay, well, let me consider those neighbors of each of my neighbors. And I'm going to ask the question, is it better to take the existing path that I have to get to that neighbor of my neighbor, or go indirectly through my neighbor? So said differently, what that says is for the closest node to me who's connected, I'm going to do the following update. That update is going to fill in my distance vector entry to that adjacency to my neighbor, and I'm going to fill in by taking the minimum of either my current least cost path to get to that node, or the cost of getting to my neighbor using my neighbor in the least cost path to that other node indirectly, plus that link to get to that node and the neighbor. Let me say that a little bit differently. So here I am at node U, right? I have my N, and I start out and I look at all of the nodes that are currently not in this N prime, such that it's the closest, its least cost path is closest. So I start out, when I bootstrap this, I have all of my neighbors, and I'm by nature of minimum, by definition of minimum, I'm going to take the closest neighbor. Okay, so I take that closest neighbor, and I then update this working set. And now I say, okay, I update this working set. Now I look at all of the neighbors of that minimum or closest node that I just added to the set. And I say, okay, well, I have my node U. That's me. I'm running Dijkstra's algorithm. I have a distance vector estimate. I have the closest node. That's going to be my, let's see, that's going to be my W. And I add W to my set of least cost path nodes. Now, okay, so now I say, I know I have some least cost to W. So there's some path that goes to W. Let me make that a little bit longer. So I have U, and I use my distance vector, D, and that distance vector has entries in it, and of those entries, I'm going to have minimum. So this might be 5, that might be 1, that might be infinity. So this is the smallest entry. So I know that there's a least cost path between me and that node corresponding to that smallest entry in my distance vector. And I'm going to call that node W. Now that W is the closest to me along some path. That's the minimum path. That's my W. So let me draw that in as a W. Okay. So I have my W. That's the closest node, i.e. on my least cost path, because a least cost path is comprised of least segments along pathway. That's my W. Now W has some neighbors, some adjacencies. So W has some neighbors, and let's call those neighbors V. So that would be, say, V1. That would be V2, ... V sub n. So that closest node, least cost path, has a bunch of neighbors. And so the question that I'm asking is, which is closer for me to get to each one of these neighbors? Is it better to take my least cost path at the present moment to get there directly? That's at a cost of d v1, or do I go to w at a cost of dw plus this link, because each one of these v's is adjacent to w? That's c, cost of that link, from w to v1. So what is this saying? Is it better to go to v indirectly through w, or should I keep my old least cost path to get from u to v? This is dv from u to v directly. This is the least cost path from u to w, dw, and I get that from my distance vector. And this is the link cwv. So I do this evaluation for each one of w's neighbors. And if it's cheaper to maintain this path, I keep that u as the predecessor for v. If it's cheaper to go indirectly through w, my predecessor changes to get to u from v. That predecessor changes to w and is no longer back to u. Okay? So I do that each time taking each node W that's closest to me on the least cost path, and I check all of its neighbors and do this fix up. Okay? Is it better to preserve the old path to get to that node V, or get to V indirectly through W at a cost of dW plus that link cost from W to V? Okay? And so the easiest way to get comfortable with this, to manage it, is to go over an example. Okay? And so we do that, and we keep adding nodes, keep adding nodes, keep adding nodes W until we exhaust all of the nodes that we have in the network, in every router in the network. Okay, so let's take a look at this example. So this Dijkstra's algorithm is running in node U. So this distance vector is the entry in the distance vector for U to get to some arbitrary node. Now, that distance vector, in this case, is going to have an entry to get to U, an entry to get to W, to V, to get to W, to get to X, to get to Y, and to get to Z. So this distance vector in U is going to have an entry for all of these nodes. There are 1, 2, 3, 4, 5, 6 nodes. So you're going to have 6 entries in the distance vector. And this distance vector is, in this iteration of Dijkstra's algorithm, is a distance vector in node U. Okay? And so for each one of these distances, the source is always going to be U. So it's the distance to get from U to U, from U to V, U to W, U to X, U to Y, and U to Z. Okay? So we start out with our blob, I like to call it, and it's going to start out just with node U. So I'm going to draw a dotted line around node U, and I like to call this growing the blob, so to speak. And so node U starts in the blob, and you initialize by setting the distance vector entries in U to the distances to each node that share a link with you. So, well, technically you share a link with yourself, and your distance vector entry is 0, right? You share a link with X, so the distance vector there, X, is going to be 5. And likewise, we have 3 for W, and we have 7 for V. But Y and Z are not directly connected to you, so those entries are going to be infinity and infinity. So we start out with that, and then we methodically add the closest node to that blob, and I'll explain and illustrate that in a moment. So here we do our initialization. We have the distance vector entry in node U. The distance to get to node V is a cost of 7, because that link cost is 7. And the predecessor along the path back to the source from V, that's P of V, that's going to be U, because the predecessor along the path to get from V back to the source, within the source is U, that's going to be U. So use the predecessor. You're going to go out this link. Okay? All right. So if we look at W, well, that's a cost of 3. The predecessor is U, right? Because that link cost is 3. And likewise, the cost to get to X in that distance vector is going to be 5, because that link cost is 5. That's how you do the initialization, is based on your directly connected neighbors. And the predecessor is along this direction. The predecessor is U. But there's no direct connection between Y and Z, so we set that distance vector entry. dy is infinity, and dz is also infinity. There's no predecessor. Okay, so now we look at our distance vector, Dijkstra's algorithm running in node U, and we say, okay, which node is closest to me? Well, here, the distance of node W, that's the entry for W, so this is for V, that's for W, this is for X, this is for Y, this is for Z. So the distance to get to W is closest, so W is the closest node to me, based on the path cost. That's what the distance vector entry connotes, is the least cost or the path cost. So you say, all right, let me now add W to this set of least cost path nodes. So I add W to it. Okay, so now I add W to it, and you can imagine now this blob, that blob grows. So I'm going to draw a dotted line to show that W gets eaten by this terrifying blob. Okay, so that's now my N prime. It has U and it contains W. So now we look at all the neighbors of W. W has neighbors X, U, X, V, and Y. Okay, so now we're going to ask the question, is it cheaper to go from U to each one of W's neighbors directly, like it used to, or go indirectly to that neighbor from W? So let's take a look at how this works. Okay, so we know that to get from U to V, it's a cost of 7. If we go indirectly through W from U to get to V, well, what is that? That's cost of 3 to get from U to V plus another 3 through that link to get to W's neighbor V. Okay? And remember, you only do this for each node's neighbors when you do this analysis. So we add up the cost to get from U to V indirectly through W. That's 3 plus 3, that's 6. That's actually cheaper than going directly through this link at a cost of 7. So you're going to change that. It's going to be a cost of 6, and the predecessor to get to V is no longer U. It's now going to be this way up top, going indirectly through W. Okay, so let's take a look at that. Oop, did the others. So it's going to be a cost of 6 going indirectly through W. So let's take a look at the other neighbors. So we have U. W doesn't change because it's its own neighbor at a cost of 0. So let's look at X, W to X. So when we go from U to X, it's at a cost of 5, where the predecessor along the pathway from X to get to the source U, that predecessor is directly to U through that link. And so is it cheaper at a cost of 5 to go from U to V, from U to X? Is it cheaper to go from U to X at a cost of 5, or to go from U to X indirectly through W? So that's a cost of 3 plus 4, that's 7. That's more expensive, so it's cheaper to go directly through this link from U to X. So that takes care of X. Let's look at Y, this other neighbor of W. So if we look at that, we say, okay, to get from U to Y, well, that's infinity. They weren't directly connected in the beginning. So is it cheaper to go from U to Y at its original cost at infinity, or is it cheaper to go indirectly through W? Now, if we go indirectly through W, that's 3 plus 8, that's 11, where the predecessor for Y to get to U along the path is going to be W. So at a cost of 11, the predecessor is going to be W. And we don't have any more neighbors of W that aren't in this N prime, so we stop. So let's take a look at this. So we still have this infinity for Z. The least cost path now, entry distance vector, to get to V has now updated 6, and the predecessor is W. Okay, that's now our new pathway to get from U to V is going to be indirectly through W. Likewise, for this path to X, it has not changed because it's cheaper to go directly to X rather than indirectly through that neighbor W. And lastly, to get from U to Y, instead of an infinite path cost, it's better to go indirectly through W at a cost of 11. So the predecessor of Y is now W along the path to U. Okay, and Z remains infinity. So now we continue this and we say, okay, what is the closest node that we haven't yet considered? Now we'll notice the path to get to X is the closest node in terms of cost. So we're going to add X to the set, and we add X to the set. Essentially, once again, we're growing the blob. This terrifying blob now encompasses U, W, and it just now swallowed our node X. Okay, so now that we swallowed our node X, we're going to consider X's 3 neighbors, or X's 4 neighbors. U is a neighbor of X, W is a neighbor of X, Y is a neighbor of X, and Z is a neighbor of X. But if we look here, if we add if we add x to the blob, okay, well, u is already in the blob, so we don't consider x's neighbor u. W is already in the blob, so we don't consider w. If we look at the other two neighbors, its other two neighbors are y and z. So now we're going to ask the question again for each of x's neighbors. Is it cheaper to go from u along its existing path to get to y, or is it cheaper to go indirectly to y through x? So we have already, to get from u to y, we go through w with a path cost of 11. So we're going from u to w and w to y. That's 3 plus 8. That's where we got that 11. The predecessor for y is w. So is it cheaper to go indirectly through x? So let's test that out. So we have 11, or we could have 5 plus 7 is 12. Well, it's not cheaper, so we're going to keep that pathway from u to y indirectly through w. So let's take a look now at x's other neighbor, z. Now, z's path cost from u is infinity, right? It doesn't have a path. So we're going to take that indirect route. We're going to go indirectly from u to x to get to z. So that's going to be 5 plus 9, that's 14. And the predecessor for z is going to be x, okay, along the path to get to u. So if we do this, okay, well, we see to get from u to v, well, that's going to be at a cost of 6, that we still keep that old entry. To get from u to y, that was what was fixed up. We keep that old entry, so we go along through w. That doesn't change. The predecessor from y back to u is going to be through w, so w is the predecessor. And lastly, z, the cost is 14 because we went indirectly through x. So the path from z back to the source u is going to go indirectly through predecessor x. So the predecessor entry is x. Okay. So now that we've done that, okay, we then look back at our distance vector and we say which node is closest. Well, the closest one is v, because v has a path cost from u of 6. That's the smallest. We have 6, we have 11, we have 14. So we're going to now add v. We're going to now add v to our working set n prime. So when you add v to the working set n prime, that's once again growing the blob. So this blob, it grows, and now we add v. See if I can draw this to the blob, right? So now it has u, w, x, and now v. Okay, so now that we've added v to the blob, or the least cost path nodes, n prime, we're going to perform that same analysis. Look at all of the neighbors of v, that closest node. So these neighbors are u, w, and y. Now u has already been added previously, so we're not going to touch that. W, v's other neighbor, has been added already, so we're not going to touch that. What remains is y. So now we're going to do this analysis for y. Okay. So currently, to get from u to y, we're going to go indirectly through y's neighbor w at a path cost of 11. So the predecessor back to the source u from y is going to from y is going to be, the predecessor is going to be w. So we have 11w. So now we say, okay, do I keep that path cost from u to w of 11, or do I go indirectly through v? So let me try this, all right? Well, if I go indirectly through v, that's a cost of 7. 7 plus 4 is 11. It's not a better path cost, so I'm going to keep the old one. Okay. So if I keep the old one, I have no more neighbors of v that aren't already in n prime, so I stop. All right. So if I do this, I still have my 10. Let's see, how did I do? Oh, ooh. That's a typo. So growing the blob, I add V. It's the closest node to U that's not already in this least cost node set, least cost path set of least cost path nodes. So let me add that V, and that's the same as growing this blob to include V. So now I look at V's neighbors, and let's see, U is a neighbor of V, W is a neighbor of V, Y is a neighbor of V. Now, U is already in the set N prime, the set of least cost path nodes, so I don't do anything with that. Also, W is in the set of least cost path nodes, so I don't do anything with that. What remains is this last neighbor of V, that is Y. Now, at present, to get to Y from U, I go indirectly through predecessor W in order to get to source U. So that path cost is this leg, which is 3 plus 8, that's 11. So I ask the question then, is it cheaper to get to Y indirectly through V, or to maintain that existing predecessor W from Y on the path back to source U at a total cost of 11? So let's take a look at this. Now, if I wanted to get from U to V, well, that's at a cost of 6, 3, and 3, and then go through V to get to Y, that's another 4, and that's a total cost of 10. So it is actually cheaper, instead of going from U to Y at a cost of total of 11, it's cheaper to go indirectly to V at a cost of 6, plus that additional link between V and Y for another 4 to make a cost of 10. And so if we look, 10 is cheaper than 11, so we're going to go indirectly to Y from U indirectly through V. Okay, so the predecessor for Y now changes to be V, and the path cost is 10. So now we still have that Z here, and we've added V, we updated that entry for V, and what remains now is this entry for Y and this entry for Z. So we're going to, again, select the closest node, and that closest node is going to be Y. Now, if we add Y, that's like, again, growing the blob. So we then grow this blob, and now that blob includes node Y. So let me just draw that blob. It's growing and growing and growing and growing. It now includes node Y. So now we take Y that we've just added to the blob because it's the closest node at this juncture, step 4, and we look at all of Y's neighbors. So Y has neighbor W, V, X, and Z. Now, if we look at V is already in the set of least cost path nodes, so we're not going to do anything with that. W at that juncture is already in the set of least cost path nodes, so we're not going to do anything with that. X is already in the set of least cost path nodes, so we're not going to do anything with that. What remains is Z. So we ask the question, is it cheaper to get from U to Z? Well, from U to Z, it's at a cost of 14. And that cost of 14 was going through predecessor X along the top here. 5 plus 9 is 14. Is it cheaper to maintain that path to get from U to Z at a cost of 14, or to go indirectly through Y? So let's see, how do we go indirectly through Y? Well, we go from U to W to get to Y from U, that's at a cost of 10 using predecessor V. So that's going from U to W to V at a cost of 6Y, that's 10. So that's 3, 6, 10. The cost 10 to get from U to Y, and then another 2 to get to Z for a total of 12. 12 is cheaper than 14, so we're going to make that update. And now the predecessor along the path to U from Z, instead of being X along the top here at a cost of 14, it's now through Y at a cost of 12. And so we're going to now go from Z, we'd go from U to W to Z to Y to Z. So now we select the closest node, that's Z, and when we select Z, once again, we're growing the blob. So the blob grows out this way to envelop or consume Z. This blob is getting bigger and bigger and bigger, and you notice now that we have now consumed all the nodes. They're in the least cost path set N, and the algorithm halts. And so each one of these optimal costs, we have from U to V indirectly through W. So that is to V goes indirectly through W. So there's our predecessor to get to U from V through W. From U to W, the predecessor along the path back to the source, that's going to be to U. So that's that predecessor. And then we have to get from U to X, that's through U. That's directly here at a cost of 5. So that's going to be, predecessor represents this link. And then we have the least cost path from U to Y is going to go through predecessor V. So that's going to be here, this link. And then we lastly have to get from U to Z at a cost of 12. The predecessor back to the source U from Z is going to go through Y. So that's this link. And so with that, we have 1, 2, 3, 4, 5, these 5 links. And this is our least cost path that we can use to get from U to any other node in the network. And our algorithm has halted. Okay, so now we construct the so-called least cost path tree by effectively tracing all the predecessor nodes. And if we have a tie, we can just choose some way to break the tie. And the key is to maintain least cost path. Okay, but just make sure you're consistent how you break ties. All right? Okay, so this is our predecessor path, and this is our least cost path that we get when Dijkstra's algorithm halts. So you could also call it the growing blob algorithm. So here's another example. In this example, we have the following graph topology, and we have U, and this Dijkstra's algorithm is running in U. So we're going to start out, N prime is set to U. We initialize all the directly connected neighbors. So we have from U going to V, cost of 2 with predecessor U, that's here. We have from U to W, cost of 5. So we have 5 with predecessor U. We have the cost from U to X is 1, predecessor is U, so I have 1. And then the others nodes, Y and Z, they're not directly connected to U. So we have infinity here for both of those least cost path entries in the distance vector. So now, first step, we select the closest node. That closest node is X because its distance is 1, right? So we add X, and now we look at all of X's neighbors. So the blob starts, it envelops X, right? It started out with U, we envelop X. So now we look at X's neighbors. We look at X's neighbor V, W, and Y. So when we look at V, we say, okay, for V, do we keep the old cost of 2, or do we go indirectly through X? If we go indirectly through X, that's 1 plus 2, that's 3. Nope, it does not improve or make the cost smaller, so we keep our old cost. So let's look at W. So if we look at W, well, if we go from X to W, that's 5. If we go indirectly through X, that's 1 plus 3, that's 4. So we're going to take the 4, and the predecessor is going to change from U to be X. So we have 4 and X. Let's take a look at X's other neighbor, Y. So the path to Y, well, that was infinity. So it is more fruitful to go from Y indirectly from X. So that's 1, 2, that's 2. So we have 2 to get to Y is the cost, and the predecessor is going to be X. Okay, so now we're done with all the neighbors of X that we just added to the blob. And now we look at the next closest node. That next closest node, we're going to choose Y. It's 2. You could certainly choose Z, but we're going to choose Y. We're just going to choose the alphabetic character that's closest to Z, if we make our tiebreaker that way. So we choose Y, and now we've grown the blob to now include Y. We're adding Y to that set N prime, and now we consider all of y's neighbors. So y's neighbors include x, w, and z. Now, x is already in the set of least cost path nodes, so we will not consider x, but we will consider w and z. So if we look at y's neighbor w, okay, well, the cost from u to w is currently 3. And how you get from u to w is, no, cost from u to w is currently 4, this entry. So the cost from u to w is 4 with predecessor x. So we'd go typically 1 plus 3 is 4. That's our least cost path. Is it cheaper to go indirectly through y? If we go indirectly through y, it'd be a cost of 1, 2, 3. And that is cheaper. So we write down the new predecessor y here. And that's a least cost path. That distance updates to 3 because it's cheaper. Okay, so now let's look at y's other neighbor, z. Now, currently, z had a path cost of infinity. So it is more fruitful to use that path indirectly from y to get to z from u. So, okay, it was infinity. So if we go indirectly through y, that's a cost of 1, plus 1 is 2, plus 2 is 4. And that's a total path cost of 4. And the predecessor to get from source u to z, that predecessor from z is going to be y. Okay, so we're done with all the neighbors of y, and now we look for the closest node. That closest node is going to be v, right? So we add v to the set of least cost path nodes, and that essentially grows the blob once more. So the blob grows to envelop v, and we're now looking at all of v's neighbors. So let's see all of these neighbors. V has a neighbor u, a neighbor x, and a neighbor w. Now, v's neighbor u is already in the set of least cost path nodes, so we don't consider that. V's neighbor x is already in the set of least cost path nodes, so we don't consider that. What remains is v's neighbor w. So we ask the question, all right, well, the least cost path from u to w is 3, right? So we went from here, u, that's 1, 2, 3. It's a total of 3, and the predecessor was y. And so we're asking, is it cheaper to go indirectly through v? Okay, so if we go indirectly through v, that's 2 plus 3, that's 5. No, it's not cheaper. So we're going to keep that predecessor y, and we're going to keep that path cost of 3 because it's cheaper. All right, so we bring down that 3 comma y. And so v's other neighbor, that was w, and that was v's last neighbor. So there are no more neighbors. All right, so now let's look at the next closest node. That next closest node, say we have 3, we have 4, that's going to be w. So we're going to add w to the set n prime of least cost path nodes. So we have w. When we add w, we're now growing the blob yet one more time, and that blob is the set of least cost path nodes. So there's w. All right, this is getting a little bit large. The blob is a runaway. So w's neighbors we'll not consider. W is a neighbor to v, to u, to x, to y, and to z. Well, w's neighbor v is already in the set of least cost path nodes, so we can't evaluate that. We leave it alone. W's neighbor u is already in the set of least cost path nodes. Okay, so we're not going to do anything with that. W's neighbor x, same deal. W's neighbor y, it's also in the set of least cost path nodes, so we're not going to do anything with that. So what remains is w's neighbor z. So then we ask the question, is it cheaper to get from u to z? And at that juncture, the cost to get from u to z is 4 with predecessor y. So that means we're going to go from u here to x, so that's 1 plus 2 plus another 2 is 4. Is it cheaper to go indirectly through w? So let's see the cost to get to w at that juncture from u to w is 3, plus another 5, that's 3 and 5, that's 8. So that would be 8. Well, 4 is cheaper than 8, so we're going to keep this least cost path of 4 to get from u to z, so the predecessor remains as y along here. So we're going to go along the bottom still to get from u to z. All right, so now we add z, what remains, the closest node. we add z to the blob, and essentially we grow the blob one more time. So there's our blob, and that blob has now consumed all of our nodes, and we're done. And so we look at all of the predecessors, and we write them down. So we have 2u, right? Predecessor to u from v is going to be this link at a cost of 2. We have predecessor for w. It's y. The predecessor is y at a cost of 3. Okay. So now u to x is going to be, predecessor is u at a cost of 1. So it's going to be this link. Likewise, we have u to y. It's going to be, predecessor is x. So that's this link at a cost of 2. And then finally, z, u to z, the predecessor is y at a total cost of 4. So these links are the set of links on the shortest path. And we take all of those results here, to form our so-called shortest path tree. And now we have a path, a shortest path to get from you to any other node in the network. And so now, if we were going to cook this down into a forwarding table and update the forwarding table at each of the routers, we would say, okay, if I'm router U and I have a destination address V, I'm going to go out this link, out that port for that link between U and V. If I have a destination address of X and I'm at router U, I'm going to forward out this port along this link, UX. If I have a destination address of Y that's seen by datagram in router U, and that destination address with that subnet address is Y, then I'm going to go through this link UX, because that's how I get there. Okay, so if I have a destination address of W, I'm going to go out the same link. If I have a destination address of Z, I'm also going to go out that link. And so each router is doing that same computation, Dijkstra's algorithm, and for each of the destination addresses, it's going to have the appropriate link identified. And in aggregate, those switching decisions, those forwarding decisions, wind up with this datagram making it to its final destination. Okay? All right. So that's Dijkstra's algorithm, another example of so-called link state routing algorithm. Let's take a look at distance vector algorithms. Distance vector algorithms use the so-called Bellman-Ford equation, or Bellman-Ford update. And so we also have a distance vector, and this distance vector dx is the least cost path from some node x to some node y. And what this algorithm does, it's an iterative update, and in this, you only get the distance vector from your neighbors. And so what you're doing is asking the question. So let's say I'm a node here, and I am node x, and I want to get to some node y. Now, of course, I have a current version of my least cost path to get from x to y. And what I'm asking in this question is, I know that I have a neighbor, right? And that neighbor is connected to me. That node V is connected by some link. And because I know that link to my neighbor, it has a cost of C of X V. I know that cost. But inside of node V, yes, it is my neighbor. It has a distance vector, and its distance vector tells it the cost to get to Y. So V has a cost dV, comma Y. That's this distance. The cost of getting from V to Y. V knows that. And V sends that to each one of its neighbors, and I'm one of its neighbors. I also have my distance vector, and I know dx, comma Y. I know this distance, right? The cost to get from X directly to Y for whatever path it's going to take that I currently have. So the question I'm asking with the Bellman-Ford is it cheaper to use the old path that has a cost, dx, to get to y, to get from x to y, or is it cheaper to go indirectly through one of my neighbors to get to y? And so the cost of my old path is dxy. The cost of the new path is the cost of this link between me and my neighbor, plus the distance vector for getting from V to that destination Y. And it does that for each one of the neighbors V that I might have. So I'm going to take that neighbor that minimizes that sum, or if that minimum distance is my old path, I'm going to keep that. Okay, so that's what the Bellman-Ford update does. So let's take an example to illustrate what that consideration is with the Bellman-Ford update. So here we have distance vector dv to get to z. So to get from v to z is a distance of 5, right? That distance of 5 is 2 down here, right? Plus 1 over here, and another 2 here. 2 plus 1 is 3, 3 plus 2 is 5. And to get from x to z, well, x to z is 3. So from x to z is along here, cost of 1, and then up here, cost of 2. 1 plus 2 is 3. And to get from w to z is going to be 3, right? That least cost path. So that's w down here, cost of 1, to z, that's 3. So we have these distance vectors in node v to get to z, node x to get to z, and node w to get to z. We know what those costs are. So now, if I want to get from node u to z, I could get there either directly, how I already know how to get there, or I could get there indirectly through one of my neighbors. So what is that? All right, well, let's look at my neighbors. I could use neighbor v, I could use neighbor w to get to z, or I could use neighbor x to get to z. So if I consider each one of my neighbors, I say, okay, well, I can go from u to v, cost of 2, and then I add to that the distance vector from v to z, which I already had was 5. So that's this first equation. That's going along that first path, right? That's going from u to v. That's along here, right? I could also take this alternate path indirectly through my neighbor x if I'm u. So I'd go from u to x at a cost of 1 plus another 3. That's a total of 4, right? So that's this consideration. This last consideration is to go through my neighbor w. So I could go along here. That link cost is 5 plus another 1, 2, another 3. That's a total cost of 8. So I have 2 plus 5 for the alternative of going from u through neighbor v to get to z. I have 1 plus 3 for the alternative of going indirectly from u to neighbor x to get to z, or I could go from u indirectly through neighbor w to get to z. So of course, the minimum of these is to go through neighbor x at a total cost of 4. So the node achieving the minimum is the next hop in the shortest path, and we use that in the forwarding table. Okay, so let's look at the distance vector routing algorithm. At each step in the algorithm, we have our distance vector. And with this distance vector is now an estimate of the least cost path from x to y. Now, each node maintains a distance vector. Again, we're going to have an estimate to get from that node as a source to all the other nodes in the network. So what does a node know? It knows the cost to each one of its neighbors. So if I'm u, and I have v here, and I have x here, I absolutely ground truth know what the cost is between me and my direct neighbors. I also maintain not only my distance vector, du, to get to some node y, I also get the distance vector of each of my neighbors. So I'm going to get this distance vector dv to get to some other node y, and I'm also going to get this distance vector from my other neighbor, and we'll call that dx to get to some other node y. Okay, so if I have the distance vector of my neighbors, and I have the cost of the links, cuv, and the cost cux, I have the cost to get for each link between me and each one of my directly connected neighbors, then I have everything I need to do this Bellman-Ford update. So I have the cost to get to each of my neighbors, so u to w, u to v, u to x, plus I have the distance vector for each one of my neighbors. That's du, dv, dx, and dw. I use all that information in the Bellman-Ford update to get the least cost neighbor. So which neighbor is going to give me the least cost path if I sum together that link cost to get to that neighbor and then use the neighbor's distance vector to compute the rest of the path cost. Okay? All right. So let's take a look at the key idea. From time to time, periodically, each node is going to send its own distance vector estimate, not as a link state broadcast to all the nodes in the network, but it's only going to send it to its immediate neighbors. So what happens when you receive a distance vector from a neighbor? You're going to update your own distance vector using the Bellman-Ford update equation. And that's the Bellman-Ford. So this thing is reactive. It's triggered. You update your distance vector if one of your neighbors' distance vectors updates. And that's demand driven as that change happens. So what triggers a change in the neighbor's distance vector? Well, one of its neighbor's distance vectors change, or it has a periodic timer to just do the update periodically. So under minor natural conditions, this estimate is going to converge to the actual least cost path. And what ends up happening is this information, it washes across the network. So if I have U, I have V, I have X, I have W, I have Y, I have Z, for example, and let's say I have them connected through some topology, right? So eventually, if Z sends its distance vector and Z sends its distance vector to this neighbor, and this one sends distance vector to each one of its neighbors, and these send distance vectors to each one of their neighbors, eventually information about this part of the network is going to make its way to that node. And that happens all across the network. So after all of these local exchanges of distance vector information, eventually it washes across the network and all these updates occur and it converges down to the actual least cost path, the actual distance vector. Okay. That's why it's called an estimate. It's no longer an estimate once things stop changing and it settles down or converges to a value that's no longer changing. That's the actual least cost path. Okay. So distance vector routing algorithms are iterative and asynchronous. Each local iteration that triggers this update is triggered by two things. A local link cost change, so you perceive as a node that the link cost has changed, maybe there's more traffic, more congestion, or what have you, or you get a distance vector update message from a neighbor. A neighbor has changed its distance vector, so it's sending out a new version of it to each one of its directly connected neighbors. This algorithm is distributed, so each node notifies only its neighbors when its distance vector changes, and the distance vector can change because of the link cost change, in addition to getting distance vector update. So you wait for a change in either local link condition, link cost, or message from your neighbor. You recompute your estimate, this Bellman-Ford update, and then if your distance vector has changed, you notify each of your neighbors of this change by sending them the new version of your distance vector. Okay, so let's take a look at a very simple example for this. And so here in this table, we have the table for each node in this network. This is for node X, this is for node Y, and this is for node Z. So let's take a look at how we'd read it. This is the cost to get from node X to node X, from node X to node Y, and node X to get to node Z, and this is from the perspective of node X. So you notice here, node X does not know how to get from Y to X, from Y to Y, Y to Z. Those entries are infinite. You only know the link cost for all your directly connected neighbors. So X is directly connected to Y at a cost of 2. So we have X on Y, that entry is 2. X is connected to itself at a cost of 0. You don't have to have any links that you traverse. And X is directly connected to Z at a cost of 7. So this entry to get from X to 7, the cost is from X to get from X to Z, the cost is 7. And likewise, for the table for router Y, or node Y, we have infinity everywhere except for this entry for Y. That's Y's distance vector. And so to get from Y to X is a cost of 2. So here we have 2. From Y to Y, it's a cost of 0. Just cost of 0. To get from Y to Z is this link cost 1, so we have 1 everywhere else is infinity. Likewise for z, to get from z to x is a cost of 7 along here. To get from z to y is a cost of 1. To get from z to z is a cost of 0. Okay, so these entries, it starts out because these tables get built in the beginning due to link cost. So these distance vectors start from some initial condition and they're set at some point to their link cost values for the directly connected neighbors. So now what happens, node x sends its distance vector, that's this row of the table, to node y and to node z. So x is going to send this 0, 2, 7, 0, 2, 7, its distance vector. It's going to send that to y, and it's going to send that to z. Likewise, y is going to send its distance vector to 0, 1. It's going to send that to x, and it's going to send that to z. Likewise, z is going to send its distance vector 7, 1, 0. It's going to send that distance vector to x, and it's going to send it to y. Okay, so let's take a look at what happens in the perspective of node x. And we're going to just cover that node and not going to do the others in the interest of time. But I'll leave it to you as an exercise. It's really, really important to understand for this network what this update is and how you arrive upon it. So let's take a look. So node x gets the distance vector from y. It gets that 2, 0, 1. So it gets that 2, 0, 1, fills that in. It knows it's from y. It also gets the 7, 1, 0 from z. So that's the distance vector from z. X gets the distance vector from each of its neighbors. So now x's old distance vector started out as 0, 2, 7. X is going to now update its distance vector using the Bellman-Ford update because it has its own link costs that it knows here. It has the distance vectors from its neighbors. So it's going to ask the question, is it cheaper to go indirectly through my neighbor or to keep my old path? Okay, all right, so let's take a look. So we have here to get from x to x is 0. That's still the least cost path. Now to get from x to y, what can we do? We can either keep our path cost to get from x to y, that was a cost of 2, or we can go from x to y indirectly through z. So if we go indirectly through z, it would be 7 plus 1, that's going to be 8. It's much cheaper to keep my old path cost by keeping my old link going directly through my link through y. So I asked myself the question, is it cheaper to maintain my existing path or to go indirectly through z? Likewise, when I want to go from x to z, I can either go from x to z from my previous link through 7, or I can go from x to z indirectly through y. Now, if I go from x to z, well, I go from x to x and go to z, or I can go indirectly x to y to get to z. That's a cost of 3. It's cheaper to go to z indirectly through y. So let's take a look at this. So for getting from x to y, I can say, all right, do I take the link cost to get from x to y by going from x to y, and then from y using its distance vector to get to y, because that's the distance vector of my neighbor. Now to get from y to y is 0. So I say, okay, is it link cost of 2 plus my y to y at a cost of 0? So I go through this link and then use that distance vector to get to y. Or I could get to y by going through this link, x to z, that's at a cost of 7, and then I go from z to y, that's at a cost of 1 or 8. So it's cheaper to go from x to y through that link to y, so that's going to be a cost of 2. And I have a cost of 2. That's the minimum. So this next example, as I said before, well, if you want to go from x to z, what can you do? Well, you can go from x to y and then use a distance vector, the current path to get from y to z, as a cost of 1. So that's going to be from x to y, that's a cost of 2, and the distance vector entry to get from y to z is going to be that cost of 1. So that's plus 1. 2 plus 1 is 3. Or I could take the cost of going from x to z, that's going to be 7, right, to get from x to z, the cost of 7 here, or from x to z at a cost of 7. And then after that, I use a distance vector for z to get to z. It's a cost of 0. So 7 plus 0 is 7. So it's much cheaper, because it's a cost of 3, to go to Z by going first indirectly from X to its neighbor Y, and then using the distance vector for that path to get from Y to Z of cost 1. And so I write in a 3 here. So now we notice here, from the first time instant to the second time instant, the distance vector of X changed from 0, 2, 7 to 0, 2, 3. So what does X do? It then broadcasts this, or sends it to each one of its neighbors, Y and Z. Okay, so I'll leave it to you to fill in the rest of the tables here. It's really, really important that you do that to understand how this all works. Okay, so let's briefly, and probably finish up with this, consider the complexity of link state routing versus distance vector routing. And with link state routing, of course, we have n nodes, and we have some number of links, and that link is proportional, number of links, big O from algorithms, of n times e, the number of nodes times the number of edges. Now, this has to do with the messages that are sent, because if you're doing link state broadcast, well, each node is going to be sending messages over every single edge, right? So if you have a node here, if you have a node here, have a node here, well, each node, when you're doing link state broadcast, you're sending over every single edge. So this node is going to send over that edge, and that edge. This node is going to send over that edge, and that edge, and that edge, right? So you're going to multiply, in terms of the message complexity, the number of nodes times the number of edges. So this link state message complexity can be very high, because everyone is sending over every single link, because you need to broadcast to every node in the network what your link state is. And that can consume a fair amount of bandwidth if you have a very large network, a lot of nodes and a lot of edges. Now, distance vector, it localizes the exchange of information. You're only sending information over links with your neighbors. You're not sending it to everyone, broadcasting. You're only sending to your local neighbors. So here, if you're broadcasting, you have to set up a spanning tree, and then establish a path to every other node, and then you're going to have to send over that path, right? Distance vector, it's only between your adjacent neighbors. Now, the speed of convergence in link state routing, it's big O of n squared, where n is the number of nodes. And that comes from the fact that you're iterating through 2 loops that iterate through all your edges. You're going through each node. So each node, you have a while loop, and there's on order of n nodes. And then for each node, you're taking a neighbor node, W, and you're looking at each one of its neighbors, and that's on order of n. So n many times, you're doing something n times, that's n squared. And so link state routing algorithms have a complexity runtime of big O of n squared, where n is the number of nodes. Now, distance vector routing, its convergence, it varies, because it takes a lot of time for that information to wash across the network, right? It doesn't converge, because you might update your distance vector routing, distance vector, you might trigger someone else to update, then you send it to your neighbor, and they send it to their neighbor, and they update, and they send something back to you, and then you update. And so it takes a lot longer to settle down to converge when you're distance vector routing. And you can also have what's called the count to infinity problem, right? There might be routing loops, and you end up keeping increasing the path cost, because they keep bouncing back and forth these sort of dueling distance vector messages to one another. You send it to your neighbor, they update, they send back to you. You update, you send back to them. They update, they send back to you, and so forth. Robustness. So link state routing, you can advertise incorrect link costs, and if you do that, because it's broadcast, it sort of messes up everyone's depiction of the network, and suboptimal routes are calculated. Each node computes only its own table, right? And so if you broadcast incorrect information, you have no way of hearing directly, so to speak, from some other node. You're kind of trusting that everything is sound. Distance vector routing algorithm, you can advertise incorrect path costs. And so you can end up propagating incorrect information to the far reaches of the network, right? Errors propagate through the network in distance vector routing. Okay, so we're going to stop there. And we will pick back up on Tuesday with routing as it pertains to so-called autonomous systems, which is a unit, a much larger unit that has a number of routers in it. And we will take a look at what this looks like leading up to what you might have in a large service provider. So with that, please stay safe, stay healthy, and I will see you on Tuesday.